This is a walkthrough of Friday's practice exam, which is on forces. Number 1, a 5, 12, 13 triangle. A right triangle is wedged between the wall and a circle. The circle is touching the left wall, the floor, and the triangle. The triangle is touching the circle and the right wall. Triangle has a mass of 100 grams. Circle has a mass of 60 grams. What is the contact force between the circle and the triangle? They're touching right here, pushing on each other. What is the contact force between the triangle and the right wall? What is the contact force between the circle and the left wall? What is the contact force between the circle and the floor? So the key here is we have to get this force diagram correct. So we have to invest some time thinking about the forces. Let's start with the triangle. So let's isolate the triangle. What's pushing or pulling on the triangle? Well, we're still in the gravitational field of the Earth, so the force of gravity is pulling it straight down. We can calculate that because we have the mass. The wall on the right is pushing the triangle to the left. Right? Walls can't pull, they can only push. So there's a force from the wall. It's a normal force, but let's call it F sub wall. The circle is pushing the triangle up and to the right. And it's perpendicular, it's normal to the hypotenuse. It's a right angle right there. And we're going to call that F contact. These two, both contact forces are normal to the surface. The force wall is perpendicular to the wall. Force contact is perpendicular to the hypotenuse of the triangle. The sum of three vector forces must be 0 because the triangle is not accelerating. To get the sum, we need the angle. We need the angle this contact force makes with the horizontal. So let's take the original diagram and sketch some lines on it. First, perpendicular to the hypotenuse at the contact point right there. And then let's draw a horizontal line through that point. And we'll get some angles. So this pointy angle down here, 5/13 arc sine, that's 22.62 degrees. Let's put that on the diagram. Now this is a horizontal line. It obviously makes a right angle with the wall. Let's put that in. And this normal, by definition, is normal to the hypotenuse. So let's put that right angle in. Okay, now we have to get the angle this vector makes with the horizontal. That's 22.6. This is 90 minus 22.6 because it's a right triangle. And if you go up to this right triangle, this little one here, this has to be 22.6. So let's put that in. We'll squeeze it in there. There you go, 22.6. So now we can put it on the diagram down here. That angle is 22.6 degrees, and now we're on our way. The downward force balances the upward force. In the vertical direction, the upward force is the contact force times sine of 22.6 degrees. We want this component, the vertical component, the opposite component. We set them equal. Set them equal. F gravity is mg, which is 1 Newton. So this is 1 Newton. So this component has to be 1 Newton, and that makes Fc 2.6 Newtons. So we have the contact force between the two shapes, 2.6 Newtons. In the horizontal direction, Fc cosine 22.6 must balance F wall. Substituting in the numbers, 2.6 Newtons for Fc. Punching the buttons on the calculator, cosine 22.6 degrees, we get 2.4 Newtons for F wall. So that's part A and B. Now we can focus on the circle. What are the forces on the circle? Gravity's down. The normal force from the wall on the left, pushing back to the right. Normal force from the floor, pushing up. And we also have the triangle pushing on the circle. The contact force that the triangle exerts on the circle is equal and opposite the contact force that the circle exerts on the triangle. So we have down 22.6 degrees below the horizontal to the left. We can put that angle on the diagram. So now we just set the forces in the x direction equal to each other and the forces in the y direction. In the horizontal direction, we have F wall to the right, and we have Fc cosine 22.6 degrees to the left, and we're going to get the same answer we got for the other wall. 2.4 newtons. In the vertical direction, we have the normal force up. Down, we have the weight of the circle itself, but also the triangle is pushing the circle down. There's some component. So the normal force is up. Down, we have Fg and Fc sine 22.6 degrees. And those balance because it's not accelerating. And we plug the numbers in and we get the normal force must be 1.6 newtons. But we know that's what it has to be in advance because that's the weight of the triangle and the circle. And this normal force is holding them both up. The triangle is not touching the floor. So the normal force on the circle must be the total weight, 1.6 newtons. We have the answers. We're done with problem 1, but let's really make sure we understand. Let's focus on the triangle only. Those are the forces on the triangle. The contact force from the circle, the downward force of gravity, the leftward force from the wall. And if we break this contact force into x and y components like this, we can see that the net force is 0. Now the circle, forces on the circle, wall pushing 2.4, gravity 0.6 down, normal force 1.6 up, and the triangle's pushing on the circle this way at 2.6 newtons. And if we break that 2.6 Newton force into its horizontal and vertical components, we can see that the force is clearly balanced. 2.4 this way, 2.4 that way, 1.6 up, 1.6 down. We're happy. Problem 2. Tablecloth is pulled out from underneath the plate. The plate moves 2 centimeters to the left. As a result, the plate was in contact for 0.08 seconds while being pulled out. What is the coefficient of kinetic friction between the plate and the tablecloth? What are the forces on the plate? What does the plate know about? Let's isolate the plate and take it out of there and say, what are the forces on the plate? We have gravity, which is down. That's always good for some partial credit. We have the normal force, the contact force, which is up. Now we have to think. Imagine yourself sitting on a rug. You're sitting on the rug peacefully, and all of a sudden, somebody pulls out the rug from underneath you. Which way do you feel a force, and what force is it? What's going on horizontally? The plate is at rest, and all of a sudden it moves to the left. What was that force? Well, it's the frictional force between the tablecloth and the plate. If there was no friction, the plate wouldn't move. So friction is to the left. Let's put it on the diagram, and that's it. There's nothing else. So the upward force must balance the downward force, so the normal force is mg. In the horizontal direction, we have the frictional force equals ma. There's only one force. Frictional force is ma. The frictional force is mu kinetic, Fn. And the normal force is mg, which we got from the vertical direction. Setting all those equal, canceling the masses, we get mu k, which is what the problem asks for, is a sub x over g. We don't have a sub x. If we had a sub x, we'd be done. We need the acceleration. The plate goes 2 centimeters in 0.8 seconds. So the average speed is 0.25 meters per second. It started from rest, the final speed must be a half a meter per second. If it goes from rest to a half a meter per second in 0.8 seconds, we can get the acceleration, 6.25 meters per second each second. Or we can just use distance is 1 f at squared plus vit, the initial speed 0, distance 2 centimeters, time 0.08 seconds, solve for a. We get the same thing, of course. So now we're done. All we have to do is plug it in. Mu kinetic, a sub x over g, a sub x is 6.25, g is 10, there we go. 0.625 is the answer to problem 2 for the coefficient of kinetic friction. Problem 3, a railroad tie is in the back of a pickup truck. Pickup truck's accelerating up a hill at 12 degrees. The coefficient of static friction between the railroad tie and the bed of the pickup is 0.6. What is the maximum acceleration the pickup can go up the hill without the railroad tie sliding out? Let's isolate the railroad tie. What are the forces on the railroad tie? As the pickup accelerates up the hill, its gravity is down. The normal force from the bed of the truck, which is perpendicular to the surface, like that. The pickup's accelerating up the hill because of the frictional force between the tires and the road. Why is the railroad tie accelerating up the hill? What is the force that's pushing that railroad tie up the hill? It's the static frictional force between the bed of the truck and itself, the railroad tie. So let's put that on the diagram. That's the force that's driving it up the hill. Now we have to pick a coordinate system. And conventionally, the best idea is to put x along the direction of the acceleration. If you do that, then a sub y is 0. The force is balanced in the y direction. So let's put that on the diagram. And now we can set the sum of the forces equal to ma in the x direction and the sum of the forces equal to ma in the y direction. The angle gravity makes with the y-axis is 12 degrees right here. Let's put that in. That's 12 degrees. In the y direction, up is Fn, down is Fg cosine 12 degrees, and those must balance. There's no acceleration in the y direction because of our judicious choice of coordinate system. In the x direction, we have the frictional force, which is pure x, minus Fg sine 12 degrees. And that's ma sub x, because that's the net force in the x direction. We have this guy up the hill and then this down the hill. So we have to subtract it. Since the acceleration is a maximum, then we can set the frictional force equal to mu static F sub n, because it's almost falling out the back. So mu static F sub n is the frictional force, the maximum that the static frictional force can supply. The frictional force from the vertical direction is mg cosine 12 degrees. We can stick that in. And now we just have to calculate it because the m's cancel and we know what mu static is. It's given. It's 0.6. So let's substitute in the numbers. The maximum acceleration, u static, g cosine 12 degrees, g sine 12 degrees. Substituting in the numbers, we get 3.8 meters per second squared, and that's the answer to problem 3. On to problem 4. We have a 5 kilogram mass and an unknown mass. The pulley is light, turns without friction. When the system is released, it takes the 5 kilogram mass 1 second to fall 50 centimeters to the floor. What is the tension in the cord? What is the unknown mass? Let's start by getting the acceleration of the 5 kilogram mass. It travels 50 centimeters in 1 second. The average speed is 50 centimeters per second. It started at rest, so its final speed must be 1 meter per second because the average of 0 and 1 is a half. If it goes from rest to 1 meter per second in 1 second, the acceleration is 1 meter per second squared, 1 meter per second every second, or we can just use distance is 1/2 at squared plus vit. Distance is a half a meter, time is 1 second, solve for a, and we get the same thing, not surprisingly, 1 meter per second squared. So now we can isolate the 5 kilogram mass, figure out the forces on it. There's the 5 kilogram mass. The forces on it are gravity, down, and tension up, and gravity's winning. The force equation is F gravity minus tension is ma, and we just calculated what a is. The mass is given as 5 kilograms, so we know the force of gravity is 5 newtons bigger than the tension. We know that the force of gravity is 50 newtons. It's a 5 kilogram mass. 50 newtons minus T is 5, so we know T is 45 newtons, and that's the answer to part A. Tension is 45 newtons. To get part B, let's isolate the unknown mass. What are the forces on the unknown mass? M. Well, we have gravity and tension, but the tension's winning because this mass is getting pulled upwards. It's the same rope. The tension is 45 newtons. The force equation for this mass is T minus Fg. Fg is mg. The force of gravity is mg, but we don't know what m is. We can substitute in the knowns. So 45 newtons equals mg. 45 newtons minus mg is ma, and we can add 10m to both sides. And we get 45 newtons equals m times 11 meters per second squared. And we can solve for m and get 4.1 kilograms. And that's the answer to part B. And that is practice exam 2.